Hello, my name is Shomo, and welcome to this course on unconventional computing. Now, this is a course I thought is sort of meant to provoke and think about a new approach to AI that synergizes past approaches with current sort of advancements in AI, deep learning, and big data. And this course really is going to look at past papers, uh, papers from different disciplines from the 1950s, 60s, 70s, 80s, decades back, when computers and AI was still in its infancy. Now that AI has naturally become quite mature, I think the time is right to take a fresh look at all these past approaches and see if there are any new insights that one can get from these approaches. So this is a special topics class, and I will just quickly share my screen. I have a few slides. So really, we are going to be looking at sort of different perspectives from complex systems or cognitive psychology, social sciences. We'll look at computational models of creativity and other unconventional models. And as I was saying, this is AI or classical AI before big data. We'll look at the heritage of computing and its interdisciplinary past. Most critically, I think we need to learn some lessons from the history of AI, what worked and what did not work, and how AI went through multiple winters. These approaches can be used to develop techniques that can inspire, or that may inspire, new explainable AI techniques. So naturally, the history of this goes right back to sort of perceptrons and cognitive psychology and things like that. Some of the approaches that we will look at is how computers can make narratives and stories. Stories are something that humans and potentially other organisms use to make sense of our complex environment. We will look at computational models of creativity and insight. We'll look at case-based reasoning, which is how humans reason. We will look at analogies, again, something that humans use a lot to reason about our complex world. We'll also look at dreams and what function they serve in the biological brains, and again, common sense reasoning, which is commonly used by humans. So looking at computational models of creativity, I mean, naturally, we are told of sort of eureka moments, Archimedes in his bathtub, Newton sitting in front of an apple tree in Cambridge and waiting for that apple to fall, and then that sparked that insight. Well, as this paper talks about, in reality, we are always building on the work of others. There is a preparation stage, then there is a very lengthy incubation stage when the idea is just at the back of your mind, and then all of a sudden there is an event and there's a sudden retrieval from memory, and then naturally we just remember that spark of insight. We don't remember all the preparation that went into it, all the incubation that had to happen before one got to that. Another example is Kekule, who discovered the structure of benzene. One night he was thinking of a snake that was trying to bite its own tail, and he realized that carbon atoms could be actually linked in a ring instead of in a linear fashion. Looking at analogies, I mean, this is again something very, very powerful. Right from when we are children, we are taught this particular analogy of so the structure of the atom, like there is this nucleus and an electron sort of circling around it, and that is very similar, or that is analogous to the solar system, where there's a sun and there are all these planets that are revolving around it. There's a force of attraction. There is sort of these planets are revolving around that, and one is more massive than the other. And naturally, the forces involved in these two systems are very different. So, but that's not the point of the analogy. I think analogies really exist to sort of anchor a new concepts that we already know, and helps us frame new knowledge in a different light. And naturally, abstracting away from what are minor details is really, really important. And what are minor details? What are the major details? I think it's really, really hard. But humans tend to do a good job in making analogies. Another analogy sort of problem that has been looked at in many papers is, for example, strings, looking at ABC to ABD, XYZ is to what? Or ABC is to ABD, II, JJ, KK is to what? And there's an excellent paper written in the 80s or 90s, I think. It's called Copycat. And essentially, the architecture of this software system is that it has a built-in concept network. For example, A is the first letter of the alphabets. B comes after that, so B is a successor. Y is a predecessor of Z, and Z is the last alphabet. And naturally, there are letters and letter groups of letters. So there's this concept network. And once the software system is presented, and I should mention that this software system is meant to mimic how the human brain builds sort of analogies and how it reasons. So that was a primary intention. So for example, ABC to ABD, and once a computer is presented with this pattern, it learns to group these into, so for example, it will learn that II is a letter grouping that could correspond to A, JJ would correspond to B, and KK would correspond to C. And then this is all happening in a workspace. And then once it does that, it naturally knows the relations between A, B, and C from its concept network. It draws a correspondence between C and KK, and it makes these groups, and then ultimately makes an inference. And the inference is done in a very interesting fashion. So it happens really sort of both in a top-down, so there's a concept network, and that drives it. But there are multiple inferences and multiple analogies that are being explored by the program continuously. So there are many ways to naturally do this analogy. So ABC to ABD, XYZ, there might be another way to sort of do that. So one way to do that is to say, well, C is the successor of B, Z is a successor of Y. What is the next one? It could be A, for example. Or you might do this in a right to left fashion and do the analogy that way. So there are many ways of doing that, and all these different ways of making analogies really sort of compete with each other. Just like in our brain, there are multiple ways that we try to sort of solve a problem. So the software architecture really tries to mimic that. This was in the 80s or 90s, and since then, naturally, the field has moved on in many different ways. And it was only a few years back that people realized that one thing that we need to do to make progress in these problems is to have new data and new benchmarks. And in particular, the creator of the Keras architecture actually proposed and created a new data set and benchmark on these similar kinds of visual analogies. So this is from the abstraction and reasoning corpus of visual puzzles. And the idea is that now that we have modern deep learning approaches which are data hungry, perhaps having tons and tons of data can enable us to create better models that can solve these kinds of analogical problems. So this is a way that actually all the work that we're going to review has been done decades back. But then there are some reasons why those haven't picked up. So part of this course is really trying to pick apart why did not these approaches really work? Is it that we don't have the data, or we didn't have the computational models, or do we need something other than deep learning? So this is something that we'll all brainstorm about. Another way to look at analogies is there's an excellent paper called the structure mapping engine. This is again mapping how the human brain looks at analogies. So for example, here's an analogy of how water naturally flows from this beaker to the beaker with sort of less amount of water in it. And this is analogous to how heat flows from a cup where warm coffee is kept, and there's a silver bar. Heat flows sort of from the coffee, if you will, to this ice cube. So intuitively, humans, even though at least I don't know the heat equation or the physics of how this works, I can intuitively understand this. And this is what I mean by common sense reasoning. So we can build, human brains can abstract out from some of these details and really get at the concept of what's really happening. We can think qualitatively about physical processes and lots of other processes in the environment rather than thinking quantitatively, which is really key to building analogies. So for example, it may mean that you build a tree-like structure. For example, flow is greater than something, and if the pressure is greater than is greater in this beaker versus this, then it will flow. And if the diameter is such and such, then it will flow from this beaker to the next. And again, in this case, in the heat flow, if the temperature of the coffee is greater than the ice cube, then the heat will flow from the coffee to the ice cube. So it's really building these kinds of qualitative models. These are really called qualitative process models. And there's again another excellent paper on that. So for example, here is something on boiling water. If the temperature of water is greater than 0, then heat flows. And if the temperature of water is equal to the boiling point of water, then it will boil. And if certain other conditions are met, it might explode. That container might explode. So it's really building these kinds of qualitative models. And then once you have a qualitative understanding of systems, then you can compare different sort of physical systems with each other. And as you will notice that there is not much machine learning or definitely no deep learning involved in this. So an open question is really, how do you incorporate modern deep learning approaches into these kinds of systems? Because much of these systems are really, I think, critical to sort of really, if AI at some point is going to mimic human intelligence, then I think these are different aspects of human intelligence which need to be captured, or we need AI to solve this. So it's really questioning what kind of approaches will work, what kind of deep learning approaches, for example, might work on a problem like this. Other sort of approaches are narratives and stories. For example, as I was saying, I mean, we use stories to make sense of our complex environment. I have a few more things to say about that in the next few slides, but then also dreams. An excellent paper suggesting that why we dream and potentially why other animals dream also is that it helps our brain sort of generalize from whatever we see at daytime. At nighttime is when we sort of try to prevent overfitting to the little amount of data that we have seen, and we try to sort of generalize to sort of unseen data that we haven't seen. So there's a theory. Again, there's an excellent paper on common sense reasoning, similar to the qualitative process models that we talked about. So story understanding. So again, an excellent paper from Patrick Winston on, for example, understanding particular Shakespearean drama, Hamlet, I think in this example. So so there's a computer program that if you give it a particular synopsis of the text of Hamlet, then it can generate a narrative arc of what actually is happening. So for example, Macbeth wants to become king, Macbeth wants to murder someone, and then this angers somebody else, and then somebody kills Macbeth. And really what this means is some of the narrative arcs are, so for example, either revenge or some kind of victory, which is not everlasting, or something about success. So the computer program can look at these pieces of text and generate some kind of understanding, quote unquote, of the narrative arc of these stories. Which really, I think, brings me to the next point of, we have talked about stories and analogies. Perhaps there's a way to combine all of these concepts. So now that we have spent a few minutes talking about AI, let us take a break and talk about something completely different. For example, Zen Buddhism. So in the 12th century AD in China, there was a Chinese monk, a Zen monk, who actually wrote a very nice sort of short story. And in Zen Buddhism, this is called a koan. So a short story, a koan is a short story that is essentially a riddle. So there are no answers, and there's just a bunch of questions, and it's just meant to help you reflect on the story and help you understand yourself. So it's basically a riddle or a puzzle. So this monk wrote the story called The 10 Bulls. The 10 bulls. And what really happens in this is there's a farmer who lives in a village, and he has a bull or an ox. And one day this bull runs away. And this farmer just goes in search of the bull. He goes to pastures, journeys across distant mountains, crosses rivers, still can't find it. After many, many days of traveling across this vast terrain, he can finally see the footprints of the bull. He can see, he can sort of perceive the bull, that the bull has been here and is probably somewhere in that region. He just begins to sort of perceive that, okay, the bull is somewhere around here. Ultimately, after many days of doing this, the farmer can finally catch the bull. Then there is a big tussle, because the bull is much stronger than the farmer. But finally, the farmer is able to tame the bull, and he rides the bull home. Again, after many days of reflection, finally the bull is transcended, and both the bull and the farmer sort of become one, and the farmer can sort of see the common source. So there's an excellent story. This is a very, very famous story in Zen Buddhism. Can anyone think of what the farmer represents and what the bull represents? So if you're just watching it online on YouTube, just maybe pause this video for a minute and try to think about what the farmer and the bull represents. If you know the answer, just shout it out to yourself. If you don't, just pause the video and think about it for a second. So, so the farmer represents all of us, and the bull is our mind. And really, the monk compared the bull to the mind because our mind is really, really hard to control. It's one of the hardest things to control and sort of really, really get some control over, especially when we are stressed or anxious. So this is a very, very powerful analogy. So this Zen monk is comparing the mind, the human mind, to the bull, and the farmer is really all human beings, or even all sentient beings on this planet. So this is a very, very powerful analogy. And then the monk actually created a very nice story of which has a narrative arc of how one can slowly, after years and years of practice and meditation and lots of other things, you can finally catch this bull. That is, you can tame your mind and you can finally bring it under your control. And finally, you realize that the mind and the self are really sort of the one and the same thing. That is, the bull or the mind is now transcended. What a very nice analogy and what a nice story. At least I think so. Now, this is what the human mind is capable of. This is what some human minds are capable of. I would argue, and some others have argued similarly, that if one day we are going to have AI that can even begin to approach the diversity of human intelligence and the diverse forms of creative output that humans can produce, then that AI probably needs to produce something similar to this. This is really, really powerful, right? So I think the abilities to generate stories and build on analogies is really, really critical to sort of human intelligence and possibly intelligence elsewhere in the animal kingdom. So I think it's really, really important to study these kinds of stories and analogies and all the different aspects of human intelligence that we have talked about so far, because these might be important to first of all to really understand and also to incorporate in future forms of AI. So another sort of track that we can talk about in this course is collective intelligence. So I mentioned that I'm not very sort of anthropocentric in my definition of intelligence. I do believe that there are different forms of intelligence elsewhere on the planet. So, for example, looking at other species and what's called collective intelligence is really, really important. And so the archetypal example that's given is sort of insects that are social in nature. So, for example, this is a termite colony. Termites are social insects. They have immensely complex societies. There are different tasks that different castes, if you will, of termites have. There's division of labor. There's a complex nest architecture. For example, this is sort of air conditioned in a way. So there are vents that will channel in air through different layers. One layer is used to grow food. Another has like a fungal colony. That's like their form of agriculture. They farm these fungus and derive food and nutrients from them. And it's a very, very complex nest architecture. Again, very similar to human societies. And what's interesting is, even though there is a queen, there is no central designer. No individual termite or no individual ant has the design for the complete structure. And part of it, how does this really happen? It really happens through, so for example, a bunch of termites or a bunch of ants will get some material together and start depositing it near the ground. And as more and more ants or termites come, they will deposit a little bit of a chemical called a pheromone on that site. And over time it will get reinforced. And slowly, with these just local interactions without a global plan, with these local interactions over time, you will see the emergence of this kind of a structure. It's called stigmergy. So I think it's very important to really understand these kinds of collective intelligence. And one way that collective intelligence has been studied for a long time is through computational models called cellular automatons. So for example, here is a very famous computer program called the Game of Life. So in the Game of Life, it's played on a grid, and each cell in that grid is either living, that's in state 1, or it's dead, state 0. So there are 2 states for each of these cells. Now, if a living cell, there are a few rules, a few very simple rules that apply to each of these cells. So if a living cell is too isolated, then it has 0 or 1 neighbors, then it dies in the next step. So there are discrete steps in the simulation. So in step 0, you start off with the initial pattern, and in step 1, you evolve. And if each cell is now reasonably surrounded, say 2 or 3 neighbors, then it remains alive. Otherwise, if it's surrounded by too many cells, maybe 4 or more neighbors in its vicinity, then it dies in the next step. And the last rule is a cell can also become living if a dead cell is surrounded by three living cells. Now, these are just rules that somebody came up with. The rules themselves are not that important, but what's important is that these rules are very, very simple, and these are all local rules. So there is no global sort of designer or global rule that says, well, starting from this initial condition, you will get sort of a particular structure. So let's just take a minute to quickly play this game on the browser. So if you go to this particular link, you can play around with this. Please be advised that it's very, very addictive, and people have spent decades playing this in sort of many different ways. So we are not going to spend that amount of time naturally. So I've gone to my web browser, and here you can here's a link to this web page, and here you can select a pattern. I will select a very interesting pattern, what's called the glider gun. So what it's going to do is it's going to populate this grid with this particular pattern, and this is just an initial condition. And then I will press play. So what's going to happen is that these are sort of similar to spaceships, and they're going to move naturally apart from each other or towards each other in this case. And something interesting is going to happen when they collide. So they're going to collide in a few steps. Right. So they just collided, and they're going to have something coming out of that. So there is another structure that just separated from them, and it's going to slowly migrate from the right to the bottom left. So we're just going to, it is just mesmerizing to watch this. As I said, it's quite addictive. So so this pattern, which you can think of like an offspring of these 2 spaceships, is now moving, and then another pattern just got generated again, and that again is going to move from the right to the left. And again, these 2 spaceships are going to move towards each other, and again there is going to be another pattern which is generated, and that's going to move from the right to the left. And this is going to repeat itself. This is going to continuously repeat itself. So it's called a glider spaceship or spaceship glider. So these are the gliders that get constantly generated, and these are 2 spaceships that move towards each other and generate these patterns. And it just goes on and on and on. So Again, no global rules that dictated that I should have this kind of a pattern or something like that. These rules just emerged from local interactions between these cells and very, very simple rules, which is how I think, which is really possibly the origin of natural intelligence in all the forms that we see on this planet. Again, these rules are made up, but we do know the rules for our sort of biological world. Uh, there are sort of naturally proteins and amino acids and DNA and RNA. How they came about, I think there are lots of theories, but we do know that naturally, at least we evolved from these very simple rules that were encoded very, very early back. Possibly arose just by chance. So again, you can spend an endless amount of time playing around with these. There are lots of other patterns, but that's one sort of insight that I wanted all of you to have from this particular game. So again, local interactions and simple rules are really, really important, and these possibly give rise to sort of collective intelligence. What does this mean for deep learning? Well, people have looked at sort of mimicking these cellular automatons and proposing new neural network architecture. So there's an excellent review paper that's the link to that is on GitHub, and here's the name of this paper. So I'm hoping somebody will pick that. But this looks at a neural network architecture that's motivated by cellular automaton. So the connections between, you can think of each cell here as like a neuron, and each is connected to 4 of its neighbors. And then there is sort of a complex function that translates the inputs that each neuron gets, and then there's an output that's fed back into its neighbors. So just like a cellular automaton, but making that concept. In this cellular automaton, there are no rules. The rule is sort of the output of each particular neuron. So all these neurons sort of get feedback from each other, and the idea is that you will get emergence of a certain behavior, instead of saying, well, I will have this rule, like if I have 2 neighbors, then do this. This sort of a continuous sort of updating scheme. Again, others have suggested looking at, so for example, these authors made a grid world again, millions of agents. You can think of each agent now as an artificial neuron. And again, they compete with each other, or they want to solve a particular task in a reinforcement learning fashion. And what's very interesting is that after time, as you let the system evolve on this grid world, these agents will develop complex characteristics like cooperation, competition, altruism, and other strategies. And naturally, none of these strategies were programmed into the system. They sort of emerged naturally from local rules. So that's about collective intelligence, and I'm really hoping somebody will pick that, because I think that's a very, very exciting field. Other concrete fields that have received a lot of attention in the 80s and 90s, but then interest is slowly reviving again, is what's called case-based reasoning. And this is how humans reason, for example. So, for example, doctors or lawyers will frequently pick out cases that they have seen in the past, and they will say, oh, okay, here's a new patient. This patient is similar to 10 other patients I've seen in the past. Let me retrieve that. Even if it's like a ballpark solution, let me retrieve that. Let me justify for why this new case is similar to 10 other cases. Or if not, let me adapt those previous solutions and previous cases that I've seen, criticize them, evaluate them, and then adapt them and make sure that I can apply whatever solution I used in the past to this new case, and then store it again. So this is what's called the case-based reasoning cycle. There's an excellent review paper on this. So again, there's a very interesting sort of approach that's probably not received as much attention in sort of this era of deep learning and AI in the current era. As I mentioned, there are other approaches, like there's this excellent paper on dreams. What is a function of dreams and what does it mean for modern deep learning? There's a very excellent paper that talks about the potential function of dreams and how we can learn from dreams and take unique insights and apply them into modern deep learning approaches. There's an excellent paper. It's there on the GitHub repository. And I also mentioned common sense reasoning that really wraps around. There's an excellent paper in the communications of the ACM by Davis and Marcus, which reviews the field on common sense reasoning. That really looks at all the stuff that we talked about, qualitative process models and things like that. And lastly, I have a few papers on explainability. Naturally, Miller in 2019 looked at what it means, what does explainability really mean, and how one can learn from the social sciences and use those insights to generate new explainable AI algorithms. So there's an excellent paper on that. Another paper on sort of building models by working with domain experts. So really this course is about, I want all of you to reflect on how we can, all the approaches that we have seen so far, how can we take inspiration from all of these? And given that now we have huge amounts of data, we have modern deep learning approaches, how can we really use all of these techniques to develop new explainable AI approaches? And I just want all of you to sort of reflect on that. So again, all the material, even my slides, are available on this particular GitHub repository. Please browse through that. And if you have any questions, email me. So we will have 5 student presentations, I think, or 4 or however many there are in this class. And somebody who is up to present will naturally present and lead a discussion on any paper that they choose. If you have any other related paper that you are really excited about, please come talk with me, and I'm happy for you to pick that paper as well. The idea really is that you will raise some interesting questions. And this course is really meant to teach you research skills, thinking critically about a paper, which is really, really hard, like picking up somebody's writing and trying to understand what's in their head, literature review skills, writing the report. These are really critical skills if you want to pursue a research career, or even if you are in industry and your supervisor says, here are 5 papers, come talk to me next week about how we can include that in our work. So that really means that you have to start from a very high level, review all these approaches, review what's been done, pick out a few approaches that are going to work and really focus on that, and then figure out what's not going to work without sort of implementing all of this stuff yourself. So there's a very, very critical skill, and it takes time to do that, but it can be learned. Some quick facts about the presentation, maybe 15 minutes for the presentation, 15 minutes Q&A for each paper. So that's the format that will be nice. About the write-up or the report, so that has 70% of your grades, and that's really the core of this thing. So pick a paper that you write, like really now or in the next few days, pick something and then start thinking about it and really sort of digging your teeth into it. Do a literature review of other papers in the field, or look at the references that paper cites, and then really reflect and write your report on how these techniques can be included in modern AI and deep learning. And as I said, the core of this course is to really help you learn how to read these papers, compare and contrast them to other papers, and then think about what it means for deep learning. And please show me early drafts, like get started on this writing process as soon as possible, because I think the report itself is due in about 7 weeks or something like that. So you really don't have a lot of time. So pick a paper that you like, Come talk to me if you're confused or need help, and then start writing out this report. Show me early drafts. I'm always happy to see that and help you with your writing. So I'm your ally in that. And then here are some writing prompts, as I mentioned. So suggest how these can be incorporated, and even think about like why these ideas were probably not successful in the 1950s or 1960s. Is it the case that we did not have the data? And then really what lessons can we learn from the history of AI? What worked and what did not work? And are there genuine disadvantages to these papers or these approaches? And there could be. That's maybe, is that why these approaches did not work? So just reflect on these, and so these are writing prompts for the report. If you get stuck on how to read papers, I know all of you are really bright, but not all of you will have research skills coming into this course, and reading papers is a skill that fortunately can be acquired with practice. So here are some very helpful links on how to read papers. And essentially it just boils down to read widely and then focus on a few papers and then take multiple passes through papers, and don't feel like you have to understand everything on the first pass. Just keep on reading it and take notes, and all those notes, by the way, well, can go into your report as well. So think of this as reading and writing sort of going along together. Lastly, this course is also meant to teach you writing skills, and this is something that I'm also quite passionate about. Here are a few links and resources, and essentially it really boils down to writing regularly and scheduling a time for writing. So here are some, here's an excellent talk by someone I really admire on sort of writing skills. I have a few copies of a book on sort of how to write a lot. Contact me if you want to borrow a copy. That's very, very helpful. And really, again, at the risk of repetition, pick a paper now and start writing your thoughts on it. Like start very, very early on this process. So it would be nice to sort of maybe actually take questions from all of you. And then maybe if all of you want to decide on a paper now, there are a few class dates. We know when the classes meet again. So I think we'll have 2 presentations or something like that each class. So we can just go through and see if anyone wants to volunteer for the next class and pick a paper and sort of present it. And really, for those who are participating, just come prepare with a question. And then, of course, everyone, please read the paper before you come to class. So before I take any questions, here is my last slide. Perhaps fittingly, a course on AI should naturally end with this picture of the Zen koan. This course is really meant to help you ask questions and be comfortable when you don't get answers. So research, a lot of the time, is you are asking questions and you don't know what the answers are. And probably some of you have taken courses where you would sort of look to the lecturer and the lecturer will be giving you answers. Sadly, in this case, I don't have all the answers, or most of the answers even. But what I can help you is, just like these Zen koans, I can help you ask the right questions and be comfortable in a state where you are constantly asking questions and you probably don't know where the way lies. But then slowly over time, this bull will come to you and you'll be comfortable sort of existing in this state of uncertainty and be constantly asking and raising questions, just like a Zen koan. So this course is just like a Zen koan. Thank you so much. And if you have any questions, just email me. Thanks a lot again.